Hello, so our lab is called Identifying the Correlation Between Medium Absorbance and Burn Time. So in creating our lab, Donovan and I wanted to find something that we were both passionate about and that's used in everyday life. So we came to the conclusion that it would be best to use a variety of multicolored pieces of construction paper. So basically, in our lab, we took different colors of construction paper and burned them using Harry's illegal 10-watt laser pointer. And we measured the different burn times for each color. So we hypothesized that the burn time would be inversely proportional with the absorbance of the light at the frequency of the laser. What?
Can you define burn time, please?
Burn time is the amount of time that the paper is exposed to the light that it takes for us to see smoke coming out from the paper. And I'll get to that later.
Sorry.
So, burn time, never mind, actually, I already defined it. So here's our setup that we used for the first portion, and then we gained the absorbance values by using the SpectraViz, and we diluted, shredded up pieces of the paper in water, and then put the vials of color water into the SpectraViz, and it gave us a absorbance versus a wavelength graph. And then we had this light intensity sensor, which we used for quantifying our burn times better, and connected that to our laptop, etc. So we used the light intensity sensor and made a graph like this, where it would record basically when the laser was on. And so Donovan, as soon as me or him saw the smoke, we just turn off the laser as fast as possible, and it would give us these peaks, and I'd just get the distance of one peak to get the time. Yes.
Why so many peaks?
Because we averaged to try and get the closest approximation.
So you move to a different spot on the paper, or do you stay in the same spot?
Yeah, different spot.
Yeah.
And because the relative value of the illumination doesn't really matter, it's just how long the light's on. And it's really obvious when it's on and when it's not. And so the sensor was just a timer that was more accurate than hand timing, for instance.
So here's an example of an absorbance versus a wavelength graph. We assigned each color of paper a different color ID. So this was just color ID 16. I don't know, it was orange, yellowish, or yeah, yellowish greenish. Yeah.
And so, scoot over here. So one of the problems that we had was that for the concentrations that we had, the way that we were getting the absorbance data, we were mixing particulate paper and water, and so depending on how the paper was configured in the water, I guess, changed the absorbance data. And so as you can see here, this is the same paper, but just as the water, or as the paper settles. And so we had to figure out some way to normalize the graphs because the absorbance was so dependent upon the concentration of the paper. And so here's our data. But for each of the way we normalized it was we had the maximum absorbance for each graph, and then we made it so that all of the maxima were the same. And so we made a normalizing factor, which just took the maximum at 1, because that's what we normalized all of the data to. So then we made, we multiplied it so that all of the max absorbances normalized were the same. And then we multiplied the absorbance at the wavelength of the laser by that factor, so we could get graphs.
The maximum absorbance occurred at different wavelengths for different colors, right?
Yeah.
Okay.
And so this is our data graphed before we normalized it, and it kind of looks like there's a trend, but the linear fit has a correlation of 0.03, and so that's not so hot. So that's why we started normalizing it. The first way that we tried to normalize it was we took the integral of the absorbance versus wavelength graph, and like we just divided the absorbance at 405 by the integral, but that still has a correlation of 0.3. When we did the normalization that I talked about earlier, the correlation went up to 0.4, which is still pretty bad. But like at that point, we just decided that our data was not good. And so then we graphed the absorbed power versus the average burn time to get the enthalpy of combustion for the paper, which was assumed to be constant throughout the experiment.
I don't know that word. Enthalpy. What?
So it's like the amount of energy it takes for the thing to combust. So for this, like this is just our math analysis on the paper thing, or on the power versus 1/time graph, which should have the slope of the energy it takes to burn the paper. And so we got that value to be 1.128 or 18, and that's not terrible. But there wasn't really an accepted value that we could find, so we didn't really have any way to do error analysis. And so...
Did it skip a slide?
Yeah, it did.
It's our sources of error, which we had a number. So first of all, the laser can become unfocused, which means that there will be like less magnitude of light. Like the intensity will be like much less. Also, there's a divot below the laser that the smoke became trapped in. So our burn time would be longer if the smoke took a while to escape from below the laser, so we could see it. And also, because the laser is so powerful, it uses up battery life really quickly, and we cycled through three sets of batteries during data collection, and four, yeah. So that like whenever we put in new batteries, like that would add a bunch of intensity to the light.
And so in all of our graphs, there was, like, even though the correlation of the data was pretty low, there was a general trend of increased burn time as the absorbance increased, or as the absorbance decreased, there was an increase in burn time. So our hypothesis was kind of true, but I mean, it's not an inverse relationship because the burn time can't go to 0. But yeah, if we were doing this again, we would probably, like, we should have more frequencies of light that we're testing. So using like a converging mirror or lens to use sunlight, and then like compared to like the total integral of the absorbance versus wavelength graph.
That's all.
But yeah.
Question?
Yes, Ben.
Oh, just on the thing you said at the end, using sunlight, wouldn't that mean then you'd have to use like spectrometry or something to split that up into individual wavelengths, and then it's white light coming in, so you have a range of
What?
frequencies?
Yes, which is why I said it would be like the time would depend on the total integral of the
Oh, I see.
absorbance versus wavelength.
Okay, yeah.
And like we were going to do that originally, but it was rainy. Like every day we had the materials checked out, and then it was too late to check them out again.
You'd also have like UV stuff.
Yeah, and that would be a problem that we would probably have to address. And yes, I agree.
Yes, sir.
Actually,
Speak up, Harry. What?
last time when I did it, like it happened the same problem happened. And what I did is I just charged it up every single time for each trail. And can I have my laser back?
Yes.
Yes.
That's on the internet, so now you will get your laser back.
Okay.
All right, thanks again, guys.
Yeah.